Okay, so what have we seen? Okay, so summary. If L1 and L2 can be solved by, now I'll call them a DFA, so deterministic finite automaton, then, okay, L1 complement, L2 complement can be solved. Okay, so what does it mean that can be solved by a DFA? It means that we can build a machine that solves that problem, that says yes whenever a string is in the language and no whenever a string is not in the language. Okay. So if L1 and L2 can be solved, then the complements can be solved. Trivial. Okay. The union can be solved. Can be solved. Okay. The intersection can be solved. And and here you just flip the yes states and no states. Flip yes and no states. Here you have to use product states. Okay, and it also turns out that L1 concatenated with L2 can be solved. L1 star can be solved. So you can do concatenation, you can do the clean star. L2 star can be solved. Okay, now I won't cover this. You can see the details in the text. Here you need another trick. Okay, and the trick here is what are called subset states. This is much harder. So product states, you multiply the number of states times the number of states. Subset states, more complicated. For example, to do the clean star, you might need subset states. Okay, so all possible subsets of the states. Well, it's a little more complicated, but it can be done. Okay. So this means that if you have any languages that can be solved by DFA, and what else do we know? Okay, any finite language can be solved. Okay, that's what started the whole discussion. We did the language that only contains 0, 1. So finite languages can be solved. If you have any languages that can be solved, you can combine them with the complement operation, the union, the intersection, the concatenation, or the clean star. So you can get more complicated languages with all these operations. Okay, and they can be solved. Okay, now we haven't proved it, but we've given all the details, all the necessary sort of details for you to go and complete the proof, or even you can read the book. Okay, but what are these? These are exactly the kinds of operations that we use in regular expressions. So let's remind you of regular expressions. So regular expressions. Okay, regular expressions. The building blocks, the starting points are finite languages. Finite. And then, you can take your finite languages and combine them with, complement, intersection, union, concatenation, and clean star. Okay, so those are the regular expressions. You take finite languages, but those can be solved. You can combine them with complements, intersections, unions, concatenation, clean star, and whenever you do this combination, we know it can be solved. So it means that finite state machines can solve all regular expressions. In fact, it also turns out that any finite state machine problem, any problem a finite state machine can solve can be described by a regular expression. But what we have shown is that finite state machines can solve all regular expressions. Wow! So any language that you can express as a regular expression, that you can describe with a regular expression, can be solved by a finite state machine. Theorem shows you the power of the finite state machine. Any language that can be described by a regular expression can be solved by a DFA. Now, we didn't give all the nuts and bolts of the proof. We showed that, at least by example, we showed you how you do complement, how you do union and intersection. We didn't get into the details of concatenation and clean star. Okay? But, at least we have sort of motivated this theorem. You can see some of the details, some more details in the text. And then if you want the full proof, you can go to more advanced texts. Okay. Now, for this reason that, any language that can be described by a regular expression can be solved by a DFA, the languages solved by DFA are called regular languages. So languages, i.e. problems solved by DFA are called regular languages. So if someone says, you have a regular language, it means that you can solve it with a DFA. Okay. So powerful machines, these simple state transitioning machines can solve any regular expression, can solve any language described by a regular expression. Wow. Hit myself on the head for that. Okay, let's erase and, see what the limits of this power are. Are there any limits to this power of the DFA? So we know that they can solve all regular expressions. What more can they solve? Turns out they cannot solve any more than regular expressions. And so now the goal is to describe a single problem that they cannot solve. Okay, and it's going to turn out that this is such a simple problem that we're going to look at the DFA and say, wow, you cannot solve this simple problem? Well then, I need more. Okay, so here we go.